Hello and welcome. Today we're continuing Chapter 7. We are starting or working on Section 7.6. We're going to learn about linear programming today. We're going to start by looking at an example. Bottled water and medical supplies are to be shipped to survivors of an earthquake by plane. Each container of bottled water will serve 10 people, and each med kit will aid 6 people. Now, if we let X represent the number of bottles waters to be shipped and Y represent the number of med kits, write the objective function, it's called, that models the number of people that can be helped. So basically, every bottle of water will serve 10 people. Every med kit will serve 6 people. So the total number of people that we can help are 10 times X plus 6 times Y, and that is some third variable Z, which is the number of people that can be helped. So this form or equation here is called the objective function. And in these linear programming problems, our goal will be to maximize this or minimize it depending on the situation. But for this situation, we want to help as many people as possible, so our goal is going to be to maximize this. However, there are some constraints. So ideally, the number of survivors helped we want to increase that without restrictions so that everyone receives the water and med supplies they need. However, the planes and ships that these supplies get transported on are subject to weight and volume restrictions. The ships and planes can only hold so much. So in linear programming problems, these restrictions are called constraints, and each constraint is expressed by a linear inequality. The list of constraints then forms a system of linear inequalities. So, for example, each plane can carry no more than 80,000 pounds, and the bottled water weighs 20 pounds per container, and the med kits weigh 10 pounds each. So if X is the number of bottled waters and Y is the med kits, write an inequality that models this constraint. So basically 20 pounds per bottle of water is 20X, 10 pounds per med kit is 10Y. So if I add those together, that can be no more than 80,000. So we can see here we've got a less than or equal to 80,000. But however, there is another constraint because there is a limit to volume as well. So each plane can carry a total volume of supplies that does not exceed 6,000 cubic feet. And each water bottle is 1 cubic foot, and each med kit is also 1 cubic foot. So that's 1 times X and 1 times Y. When we add those together, they cannot exceed 6,000, so it's less than or equal to 6,000. So the problem in this situation is we want to maximize the number of survivors that we can help, but we are limited to each plane's weight and volume constraints. So this process of solving is called linear programming. And this is based on a theorem that was actually proven during World War II, and it helped us actually win the war. So, hey, math can help in so many ways. And the idea here behind linear programming is the following. You're going to want to graph the system of inequalities representing your constraints. Okay, so you actually draw a graph of your system like we practiced yesterday and the day before. And then what you're going to do is you're going to find the value of the objective function, and this is the important part right here, at each corner, also called a vertex, of the graphed region. The maximum and minimum of the objective function occur at one or more of those corner points. And this is the key thing that was proven during World War II. And basically, here's what this means. So if you have some system of inequalities, if you imagine the cherry and grape problem we did the other day, there are all these dots inside this shaded region that are solutions that meet the constraints that we graphed. But if I want to maximize or minimize something, I don't have to check every one of these points, okay? Now, there are infinity points in this region, so instead of having to check all infinity combinations, I only have to check this point right here, 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 and here, the corners of that region. So I only have to check 1, 2, 3, 4 points, and the maximum will occur at one of those 4. as will the minimum. And that is really important because it brings down the number of points to try from infinity to 4. Now, sometimes 4 might seem like annoying to check that many, but when you compare it to the number of possibilities, 4 is way less than infinity. So what I'm going to do is I'm going to then take these constraints and I'm going to graph them. Now, there are two other constraints I want to graph, though, and these are called like real world constraints, and that is the fact that I can't have negative medkits or water bottles. So that will often be the case, as your two variables need to be, greater than or equal to 0 when you're dealing with real world numbers. So I graph this line, I graph this line, and you can see I've done that here and here. And then I graph this and this, there and there, and then I decide what region to shade for all 4 of these lines. And, I end up with this yellow region right here. So then what I need to do is I need to take this yellow region and I'm going to plug in these 4 points, just the 4 corners, into my original objective function, which remember way back was the first thing we wrote down right here. So notice I didn't graph this because it actually has 3 variables. So this isn't going to my graph, but this is then what I plug those corners into. So the thing about this one, though, is there are 4 corners, and 3 of them are very easy to identify. Obviously, this point 0, 0 is the intersection of these two. This was the y-intercept of this line here. This point was the x-intercept of this point here, which I found when I graphed them. But so I'm going to plug in those 3, but I also need to plug in this one, which you can see is like, I'm not really sure exactly where that is. It looks like it's a little more than 2,000 and right around 4,000, but I don't know exactly what those numbers are. So what I need to do is I need to find the point of intersection between these 2 lines. And the way you do that is by solving a system of equations for those 2 lines. So off to the side, I write my system. I'm going to use substitution here, so I solve it for y. And I plug that in right here for y. I distribute the 10. I combine like terms. I get the 6,000 over to the other side. 60,000 over to the other side by subtracting 60,000, and then I divide by 10, and I get x is 2,000. I plug that into either one of my 2 original equations and solve for y, and I get y is 4,000. So it looks like this point should be at 2,000, 4,000, which is looks like my lines were just a little off when I drew my lines. I guess these lines aren't perfectly straight, but it's like right there, which seems reasonable. My next step is to then plug in those 4 points now that I know all 4 points. So I plug it in to this objective function. First I plug in 0, 0, then I plug in 4,000, 0, then I plug in 0, 6,000, and then I plug in 2,000, 4,000. And then I look here, and this is the number of people that I'm able to help with my supplies, and I want to maximize this. So the largest number here was 44,000 at this point right here. And then I'm going to put my answer in context here and explain what all 3 of those numbers mean. Basically, bringing 2,000 water bottles and 4,000 med kits will maximize the number of people we can help at 44,000. So that's an example of a linear programming problem. Here's another one. I'm not going to walk through everything, but basically the general steps again. Graph all your inequalities. Shade the region of overlap between those 4. Find all 4 corners. To find this one, I had to solve this system. Then I plug each one of those 4 corners into this objective function right here to get the maximum value is 7. Make sure you actually plug in all the numbers at all the corners and to find the maximum or minimum, whichever one it asks for. And then when you're doing the online homework, just a tip. First, you're going to want to graph all your boundary lines first. So like I'm going to graph these 4 lines first, and you can make sure you keep track of whether they should be dotted or solid when you're when you're graphing them using the graphing tool, and then the last step should be shade the final region using this paint bucket tool, and then you can click on this region here and it will shade just that region. So make sure you're doing it in that order when you do the outline homework. And as always, email me with any questions.